Since its launch in 2009, NASA's Kepler spacecraft has become a prolific hunter of planets outside our solar system. It has confirmed over 1,000 exoplanets and catalogued thousands more candidates. These planets exhibit a fascinating range of characteristics, from densities greater than iron to those lighter than styrofoam, and from sizes smaller than Mercury to larger than Jupiter. Some orbit single suns, others have 2 or even 4 suns. While the sheer number and variety of exoplanets discovered is thrilling to researchers, there's still a particular desire among both scientists and the public to find a world like Earth. Such a discovery would resonate in a way that hot Jupiters and multiple star systems do not.
An artist's impression of a startling discovery deep in space.
Well, we're extremely excited. This is the biggest amount of planets that we found that look like the Earth in composition, size and mass.
This is the latest revelation in a wave of discovery over the past 25 years of new worlds. There's so much to find out about these worlds, whether the artist's impressions are right.
The American Space Agency, NASA, says it can now lay claim to the title of Defend.
Now, at a NASA press conference, the mission team has confirmed that it's worked.
Exoplanets. Our solar system has 8 planets and dwarf planets, a new category created to accommodate objects like Pluto. Pluto, now the archetype of dwarf planets, resides in the Kuiper Belt, along with other similar bodies. This classification emerged as more of these objects were discovered, distinct from the 8 major planets. Scientists, who love to categorize, also identified minor planets, over 1 million objects larger than a grain of dust in the solar system. Exoplanets, or extrasolar planets, are planets outside our solar system, typically orbiting other stars. The quest to find them dates back over 2,500 years to Greek philosophers contemplating Earth's uniqueness. Plato and Aristotle argued Earth was unique, but the idea of other planets persisted. Fast forward to the Renaissance, when Italian mathematician Giordano Bruno suggested countless suns and Earths exist, similar to our solar system's planets. Despite his controversial ideas and clashes with the Catholic Church leading to his execution, Bruno's notion of other planets lives on. Today, we no longer punish people for discovering exoplanets. The revolutionary search for exoplanets. In 1952, astronomer Otto Struve revolutionized the hunt for exoplanets with a brief 2-page paper proposing 2 techniques: detecting the wobble of stars caused by orbiting planets and observing planets transiting their stars, blocking some light. These ideas were groundbreaking, although the technology to test them didn't exist yet. Fast forward to 1995, using Struve's proposed wobble technique, astronomers discovered 51 Pegasi b, the first planet orbiting a sun-like star. This discovery won the Nobel Prize in 2019. Since then, the search for exoplanets has exploded, especially after the 2009 launch of NASA's Kepler spacecraft. Kepler's mission led to the discovery of thousands of exoplanets, filling in our knowledge of planets outside our solar system. By 2022, over 5,000 exoplanets had been found. Kepler's data transformed our understanding, showing a wide range of planet sizes and distances from their stars, far beyond what was known before its launch. One key focus of this search has been the quest for Earth-like planets, or Earth 2.0, a place where life could potentially exist. Kepler's mission. In 2009, NASA launched the Kepler mission with the goal of determining one crucial number: the frequency of Earth-like planets. They aimed to discover whether such planets are rare or common throughout the galaxy, potentially orbiting nearly every star. Kepler's mission was to measure this frequency by observing a specific patch of sky. Kepler, a 1-meter telescope, spent 4 years focused on a field in the constellation Cygnus, examining 200,000 stars. Utilizing the transit method proposed by Otto Struve, Kepler detected planets by observing the slight dimming of stars caused by planets passing in front of them. This method, though simple, provided a wealth of information. For instance, the TRAPPIST-1 system, with its small, cool red star and 7 rocky planets, demonstrates this technique. When these planets align just right, they transit the star, causing detectable dips in brightness. The frequency of these dips reveals the planet's orbital period, while the depth indicates the planet's size. This data helps scientists infer whether the planet is a gas giant or a rocky body, and estimate its temperature based on its distance from the star. Kepler's observations have significantly expanded our understanding of the distribution and characteristics of exoplanets, bringing us closer to answering the fundamental question of how common Earth-like planets are in our galaxy. Discovering Kepler 452b and nearby rocky planets. NASA's Kepler mission discovered Kepler 452b, a planet orbiting a Sun-like G-star with a period of about 372 days, similar to Earth's 365 days. This planet is slightly larger than Earth, about 1.5 to 1.6 times its size, raising concerns it might have a thick atmosphere, potentially preventing liquid water on its surface. However, the main issue with Kepler 452b is that it might not actually exist. The planet's period matches Kepler's orbital period around the Sun, suggesting it could be a data artifact rather than a real planet. With a low signal-to-noise ratio, the likelihood of Kepler 452b being a genuine planet is about 50%, and even if real, there's a 50-50 chance it's a rocky planet or a small ice giant. While Kepler 452b remains uncertain, the Kepler mission and other projects have discovered numerous rocky planets in the habitable zones of M-dwarf stars, which are smaller and cooler than the Sun. These stars' habitable zones are much closer, making planets easier to detect. For example, Proxima Centauri, the closest star to our solar system, has a rocky planet, Proxima Centauri b, in its habitable zone. This proximity makes an exciting find, as our nearest stellar neighbor hosts a potentially habitable world. The challenges of habitable zones. Around M-dwarfs. It's exciting to find rocky planets in the habitable zones of M-dwarfs, but there's a catch. Being so close to the star poses significant challenges. Stars, especially M-dwarfs, are violent and energetic. A rocky planet situated near an M-dwarf might struggle to retain its atmosphere due to intense stellar radiation. Without an atmosphere, any surface water would evaporate, leaving the planet inhospitable. The critical question now is whether these rocky planets can maintain their atmospheres. If they can, they might be habitable. If not, their surfaces would be exposed to the vacuum of space. Despite finding many rocky planets in the habitable zones of M-dwarfs, we don't yet know if any are truly Earth-like. Currently, there are no confirmed Earth-like planets in habitable zones that we believe could support life. This uncertainty is why NASA's James Webb Space Telescope, JWST, launched a couple of years ago, is so crucial. JWST can analyze the atmospheres of planets in the habitable zones of M-dwarfs. For instance, the TRAPPIST-1 system with its 7 rocky planets is under investigation. So far, JWST has found no atmospheres on the first 2 planets it observed. The third planet, which lies in the habitable zone, is now under scrutiny. If it has an atmosphere, it could dramatically increase the estimated habitable real estate in the galaxy, as rocky planets around M-dwarfs are far more common than Earth-like planets. This would significantly boost our understanding of potential habitability in the universe. Diverse discoveries. The varied worlds beyond our solar system. While 0 Earth-like planets have been found in the habitable zones of Sun-like stars, there are still exciting discoveries to share. The Kepler mission revealed an incredible array of planets that look nothing like those in our solar system. Until 30 years ago, planetary formation theories were based solely on our solar system. Now, there are numerous types of planetary systems, greatly expanding our understanding. Among the discoveries are hot Jupiters, gas giants that orbit their stars in just a few days. One such planet, HD 189733b, orbits so closely that stellar activity strips away part of its atmosphere, resulting in sideways rain of liquid glass. Kepler also found rocky planets the size of Earth orbiting their stars in less than a day. Kepler 10b, for example, is a tidally locked planet that orbits its star in a few hours, creating a scorching lava world with a surface of melted rock. In addition to these extreme examples, Kepler discovered numerous rocky planets further out, warm rocks, as well as Neptune and Uranus-sized ice giants and ocean worlds. Surprisingly, most planets found by Kepler fall between the sizes of rocky planets and ice giants, representing a new category of exoplanets. These diverse findings highlight the vast and varied nature of planetary systems beyond our own, the new classes of exoplanets. The Kepler mission revealed surprises that challenged our understanding of planetary systems. In our solar system, there are 3 distinct size categories: rocky planets, ice giants, and gas giants. However, Kepler discovered that the most common type of planet doesn't fit these categories. These super-Earths, or sub-Neptunes, are larger than Earth but smaller than Neptune, a size regime absent in our solar system. This discovery was unexpected because our models, based on the solar system, did not predict such a prevalent class of planets. In addition to these new planet types, Kepler found several other fascinating planetary configurations that were once thought to be purely science fiction. One notable discovery is the existence of circumbinary planets, which orbit 2 stars. This scenario, famously depicted in Star Wars with Tatooine's double sunset, turned out to be real. Planets in such configurations expand the potential habitable real estate in the galaxy, since most stars are part of multiple star systems, showing that planet formation can occur in a variety of stellar environments. Furthermore, Kepler found planets orbiting white dwarfs, the remnants of stars like our Sun, after they have exhausted their fuel and shed their outer layers. It was uncertain whether planetary systems could survive this dramatic stellar evolution. Kepler's discovery of planets around white dwarfs suggests that planetary systems can indeed endure such transformations. This finding provides insights into the distant future of our own solar system, where some planets might survive the Sun's evolution into a white dwarf. These unexpected discoveries demonstrate the diversity and complexity of planetary systems, significantly broadening our knowledge beyond the confines of our own solar system. Kepler has shown that the universe is filled with a wide array of planets, many of which are unlike anything we see in our solar system, challenging our theories and expanding our understanding of planet formation and evolution. The future of human civilization and the continuing exploration. Looking ahead, the discoveries made by missions like Kepler have profound implications for the future of human civilization, even if it spans billions of years. The finding of planets around white dwarfs suggests that planetary systems can endure dramatic stellar transformations, hinting at the potential longevity of planetary systems, including our own solar system, over cosmic timescales. Returning to the intriguing TRAPPIST-1 system, where 7 rocky planets orbit closer to their star than Mercury does to our Sun, we observe a tightly packed system where planets are in resonance with each other. Resonances, such as the 3.2 resonance observed in the Galilean moons of Jupiter, ensure stability and longevity in planetary orbits. This stability could be crucial for the development and sustainability of complex ecosystems on habitable planets. Citizen scientists have played a significant role in these discoveries, as seen in the K2-138 system found using Kepler data. This system's planets are in a beautiful harmonic resonance, resembling musical intervals like a perfect fifth. Such discoveries not only expand our knowledge of planetary systems, but also inspire public engagement through projects like planethunter.org, where anyone can contribute to the search for new planets from home. Looking forward, NASA's TESS mission, launched after Kepler's hardware failures, aims to discover even more planets, focusing on nearby systems. Projected to find around 12,000 planets, TESS will substantially increase our catalogue of known exoplanets and bring us closer to discovering an Earth 2.0. Though perhaps not in the immediate future, it sets the stage for future missions that could further revolutionize our understanding of exoplanetary systems and their potential for harboring life.